So let's go over the agenda today. Real simple. We're going to go over datums and geographic coordinate systems. And then we'll look at map projections and projected coordinate systems. And these are grid coordinate systems or Cartesian coordinate systems. And we'll go over a few best practices in GeoGraphix. And we'll wrap up with some questions, and I'll answer those at the end of the presentation. So let's jump right in and talk about cartography. Cartography is the art and science of map making. Been around for a very long time. Even though Columbus sailed the ocean blue in 1492, people really knew that the Earth was not flat in 1492. And so this science is quite old. A lot of strange terminology, lots of complex mathematics, although that is sometimes hidden from us by modern computer codes like Esri and GeoGraphix and whatnot. And there's a lot of competing standards and terminology out there, PRJ files, well-known text files, EPSG codes, on and on and on. And sometimes it can be a little bit confusing, but at base, it's not confusing. And I'll show you why. Well, also, errors can be costly in our business. And that's, unfortunately, if it's very easy to take a look at our house on Zillow. But when we locate a bottom hole location or a surface hole location, we need accuracy that is beyond what we see on Google Maps. Although I'll tell you, I love Google Maps. I mean, it's hard to believe that it's been out there now for, gee, probably a dozen years. But it's really changed the way folks think about GIS. So let's talk about geographic coordinate systems. Now, when you think about a geographic coordinate system, you need to think about a whole Earth coordinate system. And that means latitude and longitude. This isn't a state plane coordinate system or a grid coordinate system. Geographic coordinate systems, location is always latitude and longitude. It's described by latitude and longitude. And of course, you can see here that through the center of the Earth at 0 degrees latitude is the equator. And the prime meridian goes through Greenwich, England, and that's at 0 degrees longitude. But the Earth is not a sphere. So you can see here that if the Earth was a sphere, we would have one radius for the Earth from the poles to the center of the Earth and from the equator to the center of the Earth. Fortunately, that's not how it works. Due to centrifugal force, the Earth bulges around the equator and it flattens near the poles. So we need to create a mathematical best fit to the Earth's surface using an ellipsoid. So whenever you look at a PRJ file or you look at a well-known text file in Esri, that ellipsoid, this is what it's actually defining. So in order to create an ellipsoid, you have two radii, I suppose, a semi-major and a semi-minor axis, one from the center of the Earth to the pole, and one from the center of the Earth to the equator. There's also something called a geoid, and we won't be talking about geoids, but basically you can model a best fit to sea surface or sea level using an equipotential gravity field. This is sort of an advanced geodetic concept, but for almost all of the datums that we use daily, you'll be seeing an ellipsoid. So an ellipsoid will be defined for that datum. And that really is just a mathematical best fit to the Earth's surface. Which surface of the Earth, though? Like I said, cartography has been around for a very long time. And over time, we've been able to create mathematical best fits that are more and more accurate. So ellipsoids have become more and more accurate. In other words, the distance, the A and B distances are more and more accurate over time. With the advent of geostationary satellites, we've been able to create very, very accurate representations of the Earth's surface. But there's a lot of them out there. So this is something you know, as I talked about before here, datums are defined by ellipsoids. There's a semi-major or a polar radius. There's a semi-minor or polar radius, and a semi-major or equatorial radius defined for each datum. So remember always, this is the important thing to remember about datums. The latitude and longitude of any point on the Earth will vary depending on the geographic datum that is used to represent your surface. So what that really means is the latitude and longitude of a well in NAD 27 is not the latitude and longitude of the same well in NAD 83. And when I first got into this business, this sort of confused me because I really didn't understand what a datum was. I just thought a latitude and longitude was a latitude and longitude, and it didn't really change. But it actually depends on that mathematical best fit to the Earth's surface, which is called a datum. So we know that the latitude and longitude of a point on the surface is going to be different depending on the datum that you're using. How much? Well, you know, it depends. Now, in North America, in the U.S. especially, we do use North American datum of 1927 and the North American datum of 1983. Now, the shifts can be substantial, and it's going to depend on where you are in North America. So you can see here, if you're out in the DJ Basin, out here in Colorado, or you're in the Permian, the datum shift between NAD 83 and NAD 27 could be as much as 150 feet. And it actually gets worse. You can go up to 300 feet if you're out in California. And then if you're, you know, somewhere in western Indiana, not very much. But the error that can creep in if, for instance, you have a well in, well, the well has a latitude and longitude in the NAD 27 datum, and you're using a map, or you believe that that latitude and longitude is in the NAD 83 datum, and that's what you have your, for instance, your GeoGraphix project set up as is NAD 83, the location of that well on your maps will be considerably off. There'll be considerable error. And some datums, you know, the error will be even more. So you sort of have to remember this and be aware of it when you get a well spot or any sort of spatial data that has lat long associated with it. First thing you need to ask yourself, what datum? What datum? If you don't ask yourself what datum, you know, you will get a considerable error. Sometimes it doesn't mean that much, but when you get to 150 to 300 feet, then it's, you know, it means quite a bit. And of course, depending on where your bottom hole location is with all the horizontal wells, it could be much, much more than that. So it's good to understand this kind of stuff. Now, the latitude and longitude can be shifted from one datum to another using a number of transformation methods. If you're transforming, for instance, NAD 27 to NAD 83, just a hint, always use NADCON. These transformation methods are mathematical formulas that transform a latitude and longitude in one datum to a latitude and longitude in a different datum. Sometimes they're just pure mathematical formulas. In the case of NADCON, it's a computer code that's been created by the U.S. government, and it has about 10,000 different reference points. And they're shifted and they're used to interpolate. And that's what you use when you use NADCON. If you're presented with a number of transformation methods, and NADCON is an option, always use NADCON. It is by far the most accurate way to shift latitudes and longitudes from one datum to another. Now, datums are limited in geographic extent. We already know that they are a mathematical representation of the Earth's surface, defined by an ellipsoid, but they're limited in geographic extent. So, for instance, you would not be using the North American datum of 1927 in Russia or in Europe. Some are more accurate at high elevations, and some are more accurate at sea level, for instance. There are a lot of datums out there. There's probably well over 100, probably more than that. All of them historical. And you can see, well, you can sort of understand why. As cartographers were able to make this mathematical representation of the Earth more and more accurate, more and more datums were used. Now, lately, geostationary satellites have made the development of very accurate whole Earth datums possible. So before I said, yeah, you know, a datum is only usable in a certain geographic area, geostationary satellites have made datums, whole Earth datums that can be used anywhere on the surface of the Earth. WGS is a very, very accurate datum, but obviously we had to have satellites in order to do that. So that begs the question, exactly why don't we use the most accurate datum? And we should, actually, but there's a couple reasons why we don't. And one is an awful lot of legacy spatial coordinates are in old datums, or datums that were used in the 19th century and the 18th century, and on and on and on. There's also some legal reasons on deeds and leases and legal documents. Those latitudes and longitudes would have been in datums that are not the most accurate datums that we have in use today. So for instance, many of your GeoGraphix projects are still set up in NAD27. And if you have NAD83 well locations, you just, when you import them, you go ahead and transform them into NAD27. Because of all the legacy data in the oil and gas industry, people still do that. Although lately NAD83 has become very, very popular, basically because of state reporting requirements. Okay, so now we know what a datum is and a geographic coordinate system is, and remember, it's always, the locations are always defined by lat long. But now we need to make a map. So when we make a map, we need to project those latitudes and longitudes, those geographic coordinates, onto a flat surface or a Cartesian surface. There's a bunch of different ways that we can do that. Some of the more popular ones you can see here. There's a cylindrical projection in which the latitudes and longitudes are being projected, or the locations are onto a cylinder. There's a conic projection in which the locations are being projected onto a cone. And there's the secant planar projection in which basically the latitudes and longitudes, the surface of the Earth, is being projected onto a plane. So why so many? Well, it turns out that some of these projections are better, for instance, to use in polar areas. Some are better when used in mid-latitude areas, and some are better when they're used in equatorial areas. And why is that? Well, because map projections always cause distortion in either area, shape, distance, or angle. So a geographic, well, if let's say you had a globe that was a perfect representation of the surface of the Earth, and you were spinning it around, when you looked at two locations on the surface of the globe, there is no distortion. But whenever you project onto a flat surface, there's always going to be distortion. And it's sort of a pick your poison thing. So in some ways, let's say if you were in polar areas, you wouldn't want aerial distortion. So in a lot of cases in polar areas, planar projections are used. And you can see this when you look at maps of the world, right? You can't really see it when you look at maps of a certain area, let's say a couple townships. But when you take a look at a map of the world, you'll notice very quickly in some projections, Greenland looks huge and compared to the United States. looks about the same size as the United States. Well, you know, Greenland's only about 20% of the size of the United States. So there's always going to be some distortion. And it's like I said, it's a pick your poison thing. Some of the projections work better in or have less distortion in mid-latitudes, polar latitudes, or equatorial latitudes. The two of the real common map projections that we use are UTM, which is Universal Transverse Mercator, where the Earth's surface is projected onto 60 separate cylinders, and many state plane zones use the UTM projection. And this is especially true in states that are longer north-south than east and west. The Lambert conformal conic projection is also used in state plane zones, often in states that are longer east to west instead of north to south. So let's take a look at that. These are worldwide UTM zones. So you can see the world has been divided into 60 UTM zones. In the U.S. or North America, those zones usually are from basically zone 10 to maybe zone 13, where I am in Colorado, all the way to maybe zone 18 out there in the Marcellus. Now, state plane coordinates are the projection of latitudes and longitudes from the GRS 80 ellipsoid. So it's just another ellipsoid. Remember, that's just a mathematical way to describe the surface of the Earth. And it's projected onto a flat mapping surface that is usually defined by state law. So here are your state plane zones. And you'll notice here that states like Texas and Kansas and Oklahoma and Colorado, which are longer east to west, will use the Lambert conformal projection, map projection. And the ones that are longer north to south, like New Mexico here, will use the Universal Transverse Mercator projection. Okay, now I know what a datum and projection is, but what's the coordinate reference system? If you've used Esri applications, and I think most have, and certainly we install the Esri runtime environment when we install GeoGraphix. So we use the Esri transformation engine also. You'll see references to CRS. CRS. What is a CRS? Well, a CRS is a datum and a projection and a meridian and a unit of measure. So you have to have all of them. Although, you know, if you just have you can just be a datum, a meridian, and a unit of measure. If you have a grid coordinate system, then you'll have the projection also. But you got to have all of that. And it's defined in a well-known text or PRJ file. Again, if you've used Esri software or GeoGraphix software extensively, you'll sort of know what a PRJ file is, or a well-known text file. And then you have this other thing called an EPSG code. And EPSG codes are numeric shorthand for CRSs, for coordinate reference systems. So EPSG stands for European Petroleum Survey Group. It's a now defunct organization that came up with these numerical codes for each coordinate reference system, and there are thousands of coordinate reference systems out there. Now, how do we define a coordinate reference system? Well, in a PRJ file, you can see this is what one looks like here. You can see that there are a lot of different, there's a lot of different information in here. So you have a projected coordinate system, and this is one here, is the NAT 83 Colorado North U.S. survey feed. Now the geographic coordinate system, that's the next line, is NAT 83. So the geographic coordinate system is using the NAT 83 datum. The spheroid or the ellipsoid is GRS 1980. And the numbers afterwards would be that, I believe it's just the, actually I think that's the flattening there. But there's going to be some information after it that helps you describe the surface of the Earth. And there's an authority. There's also a prime meridian. So in the case of NAT 83 Colorado North, the prime meridian is the Greenwich meridian. So you will have, let's say you're using this in Colorado, and as you go west, longitudes are negative. So here it'd be about minus 105 west longitude. And there's units. Here it's degrees, and there's also a unit of measure for distance. And in this case, it's U.S. survey feet. And the number that you see after that, that is just the conversion to metric, to a meter. And then you'll have the projection that's being used. In this case, because Colorado is longer east to west, it'll be the Lambert conformal conic projection, as well as a central meridian, a latitude of origin. And remember, when you look at a map or you're looking at coordinates, and these are XY coordinates, they're going to be very, very large numbers, and there's going to be an origin, just like a piece of graph paper. There'll also be a false northing and a false easting, and false northings and eastings are an arbitrary distance that are added to projected coordinates so that the X and Y coordinates can be distinguished from each other. In other words, one is going to be bigger than the other, and that makes it much easier to see which is your X and which is your Y coordinate. But also it keeps the coordinates from becoming negative. So if you think about a piece of graph paper, you have an origin at 0, 0, and if the origin was always at 0, 0, then anything south would be negative, or southwest would be, well, you'd have negative X and negative Y. And that's very, very confusing, and it's also difficult for computer programs to handle as well. There's a lot of error that creeps in. So we use false northings and false eastings to ensure that all your XY coordinates are positive. You ever wanted to know that? And I didn't know that until relatively recently, actually. So what's the right coordinate system for you when you set up your GeoGraphix project? Well, it really depends on the type of vendor data that you import. IHS well locations are generally in NAD 27, but you know, IHS has well data all over the world, and all those lat longs are in some datum, and a lot of folks will just set up their projects as NAD 27 because that's where they're getting the data from, and that's the well locations are all NAD 27. However, NAD 83 and sometimes outside of North America, WGS 84 is becoming increasingly common, and that's because state reporting requirements or provincial reporting requirements, excuse me, or federal reporting requirements increasingly demand that all of your latitudes and longitudes be in NAD 83 or one of the newer whole Earth coordinate systems. This is because it's just more accurate, right? So the database coordinate system that is chosen in GeoGraphix is usually, but not always, it doesn't have to be a geographic coordinate system. But the reason why you want it to be a geographic coordinate system is because if you choose a projected or a grid-based coordinate system, in other words, your well locations have XY coordinates instead of lat-long coordinates, your project is only really going to be valid in that geographic area. So, for instance, if projects now are so huge and they span hundreds of thousands of wells, if your project spans, you know, 2 or 3 UTM zones, well, then you sort of have a problem here. Or it spans through a UTM zone, then you sort of have a problem if you set up your database coordinate system as a grid coordinate system. So it's always better if you do have latitudes and longitudes for your well locations and your other data to set up your database coordinate system as a geographic coordinate system with a datum. Now the map coordinate system, that's the coordinate system that you see on the map in GeoAtlas, is often a grid coordinate system, and it'll be a state plane coordinate system, UTM coordinate system, on and on and on. We also, in Geographics anyway, allow you to create custom coordinate systems. Just be a little careful when you do that, because in general we try to make sure everything's consistent in Geographics. But if you do choose or try to create a custom coordinate system, it may be difficult to transform those locations in other software packages because they just may not support custom coordinate systems. So if there's anything that I want everybody to take away from this little presentation today, is the most important question, or the most important question that you can ask when you're presented with a piece of data, spatial data, with a coordinate or a location, is what is the datum and projection? You need to know both. And I didn't know this either until I got into the business. But you have to know both. If you don't know the datum and projection, and then you try to transform that point into another datum and projection, and for instance, the datum that you chose for the source is not right. In other words, the original datum was NAD 27, but you said NAD 83. When you project those points into a new coordinate system, let's say it's, who knows what it is, NAD 83 State Plain, Kansas South. If you try to do that, you will have considerable error. So you must know the datum and the projection of the data that you want to bring into Geographics or any other GIS package. If you don't, you've got to guess. And if you guess and guess wrong, well, there's going to be some errors. And the errors can be pretty significant. So, know the datum and projection of your spatial data before importing it into any GIS software. And 4 pieces of information are required. When you get a piece of data or you get a file and it has locations in it, you need to know the datum and projection of the source data. And of course, you will know the datum and projection of the target coordinate reference system, because that's the one you'll be using in Geographics or in ArcMap or in any other GIS software that you're using. Oftentimes, you'll know the projection of the source data, but you won't know the datum, so you'll just have to guess. Again, you know, sometimes you can make a good guess, sometimes the guess isn't so good, but a lot of old data doesn't have this information associated with it, or was lost long ago. So you sort of have to, you know, not just import it in, you take a look at it. Nice thing to do is just put a satellite image on where you can take a look at your well spots, and if they're considerably off, especially if they're all off by the same amount in the same direction, that's an indication that you got a datum problem. One other thing I'll mention, that in Geographics you can shift your datum. So if you're bringing in, for instance, WMS or Web Map Services, and that Web Map service is in WGIS 84, which most are, and you need to shift it into for instance, NAD 27, fairly easy to do that. Just right-click on the layer and select the datum shift, and you can go ahead and shift the datum. The dialog that you'll see is very, very similar to the one that you'll see in ArcMap, but just remember, just as in ArcMap, when you shift datums, every layer on the map is going to use that datum shift. So you have to sort of remember that. Okay, so in Geographics, we do allow you to, for almost all of your spatial data types, import into Geographics and transform as you import. So you don't need to have the data in a certain datum and projection or your project datum and projection, map projection. It can be in some other datum and map projection, and you can transform it on import. But you need to know what the source datum and what the source projection